Hi again. The last video from part 1 of lecture 9 is this one. And I just want to look at claims made by products that you can evaluate using math. And when I see something like, this product kills 99.9% of harmful microorganisms, that does insult my intelligence a little bit, because it's really not giving you enough information, and then once you examine it, you might find that it's not very impressive. So let's get into it. So what does 99.9% mean? We can convert that to different ratios that might let us see it differently. So 99.9% is the same as 99.9 out of 100, because that's literally what percent means. It's a number out of 100. I would be more likely to think of it as 0.999 out of 1. And that's the same thing. We just divided both these numbers by 100. You could also see it as 999 out of 1,000 if you take this number and 100 and multiply them by 10. Either way, you get the same ratio every time. It's just you might be more comfortable thinking about it as a percent or out of 1 or out of 1,000, whatever. So if you kill 99.9%, you leave 0.1% alive. So that's 0.001 out of 1, or 1 out of 1,000. That's 10 to the minus 3, right? So 1,000 is 10 to the third power, 1 is 10 to the 0 power. So to go from this to this, it's 10 to the minus 3. So, okay, all of that, even if none of that made any sense, what should make sense is that killing 99.9% is a 3 log reduction. In other words, it's the same as dividing the population by 10 to the third power. And so, is that meaningful? Do we care about 10 to the third power? So we can look at some starting and ending populations, and we're going to get a different answer depending on what the infective dose is. For something like Shiga toxin producing Escherichia coli, where the infected dose is around 10 cells, very rarely would you ever get low enough to protect yourself against that. Because if you start with 10 to the 6th, which is a pretty small bacterial population, you'd have to reduce it more than 5 logs. So that would be 99.999% in order to protect you from that. And so here are some real starting populations. 1 gram of feces is 10 to the 14th cells. Off the top of my head, I don't remember what that is. 10 to the 6th is a million, 10 to the 9th is a billion, 10 to the 12th is a trillion. So that's 100 trillion cells per gram. And so if there's a tiny bit of fecal contamination on something, 10 milligrams, that's still 10 to the 12th. That's still a trillion bacterial cells. So a 3 log reduction of a trillion cells is still a billion cells. It's a huge number. If you leave a fingerprint on something, you're leaving something like 10 to the 4th, 10 to the 5th cells, whatever. You can use these numbers. I just want you to think about what it means. And so what if we increase it to a 4 log reduction, or 99.99%? You can just go back and think, what was the starting dose? And does this reduction get it below the infective dose you care about? And so what you could take away from this is it's important to know starting doses. It's important to know infective doses. And it's important to acknowledge that you will almost never know the starting dose or the infective dose. And so we have to do things like just use disinfectant products for the appropriate contact time. And that's often the best we can do. But if you see a consumer product making some claim about 99.9% or something, just do the math and you will be much less impressed. Thanks.